Welcome to Training Module 3, focused on the data center fuel polishing system. In this module, we'll cover the design and sizing of the system, including the types of filters used and how controls integrate to maintain fuel quality. We'll explore the human-machine interface, or HMI, which provides real-time cleanliness monitoring and ensures maintenance readiness to keep the system running smoothly. This module is mission-critical because a reliable fuel polishing system supports uninterrupted data center operations. You'll also get an overview of the Integrated Fuel System HMI, the fuel polishing skid, staged filter media, and the controller interfaces. Our goal is to provide you with a fully furnished technical education that equips you with the knowledge needed to manage and maintain these essential systems effectively. In this module, we've integrated new and critical information into a ready-to-use training paper focused specifically on mission-critical fuel polishing. We've centered the content around several key areas. First, the technical focus addresses challenges unique to Indonesia's B35 and B40 biodiesel blends, including risks posed by tropical humidity, microbial sludge formation, and water management issues. Importantly, we explain why relying solely on engine filters is inadequate for maintaining stored fuel readiness. Next, the module covers new regulatory considerations. This includes the ESDM biodiesel mandate context, evidence requirements from OJK for disaster recovery and business continuity, as well as relevant standards such as NFPA 110 and ASTM fuel testing protocols. We also emphasize ISO 4406 cleanliness targets and best practices for environmentally responsible handling of contaminated fuel and waste. We then introduce an updated calculation approach, correcting the turnover formula with practical examples like handling a 50,000-liter tank and sizing underground storage tanks at 6 times 110,000 liters. A two-zone polishing strategy, safety factors, and cleanup models are also highlighted to help improve fuel cleanliness in line with ISO standards. Visually, we explore concepts such as typical skid-mounted filter polishers, high-capacity enclosed polisher designs, cleanliness target illustrations, and multi-filter circulation setups to provide a clear understanding of equipment and system design options. Lastly, the intent of this final document is strictly technical education. It's crucial to remember that final design criteria, local regulatory approvals, equipment manufacturer limits, alarm settings, and operational procedures need to be reviewed and validated by the equipment owner, engineer of record, authority having jurisdiction, and the manufacturer. This approach ensures the training is thorough, practical, and aligned with both technical and regulatory requirements for effective fuel polishing in mission-critical environments. Here is an overview of the training module's flow, designed for both instructor-led sessions and self-paced learning. We start with the orientation, which lays the foundation for understanding mission-critical fuel readiness and explains why fuel polishing is essential to protect emergency power and ensure uptime. Next, we'll dive into Indonesia-specific risks related to B35 and B40 fuels, including challenges like FAME content, water absorption, oxidation, microbial growth, and the unique risks posed by tropical storage conditions. Following that, we'll explore the regulatory and standards framework that supports compliance and best practices. This includes guidelines from agencies like ESDM, OJK, NFPA, ASTM, ISO 4406, and evidence requirements for environmental and owner or tier readiness. Then, we cover the system architecture and process flow, detailing components like tank suction and return lines, filters, coalescing and water removal units, controllers, building management systems, and alarm configurations. The next section focuses on the mechanical skid, pump, filters, and containment strategies, emphasizing skid-mounted packages, leakage containment, and the philosophy behind maintenance drainage. We'll also delve into the programmable logic controller, PLC, human-machine interface, HMI, controllers, and sensors, covering the logic behind pump variable speed drives, solenoid valves, differential pressure monitoring, leak detection, water and flow measurements, and cleanliness instruments. Further, the training addresses ISO cleanliness standards, differential pressure monitoring, and maintenance practices, including target cleanliness levels, inline monitoring, filter loading, and criteria for changing filter media. We then move into sizing calculations with practical examples. This covers formulas and safety factors, including a 50,000-liter example, a two-zone example with 6 by 110,000 liters, and a cleanup model for real-world application. The module also covers operation, maintenance, and readiness evidence, highlighting scheduling, commissioning processes, log keeping, alarm response protocols, preventive maintenance tasks, and troubleshooting techniques. Finally, we conclude with appendices and references, providing worksheets, specification checklists, cause and effect matrices, and source notes to support ongoing learning and application. This comprehensive structure ensures that you gain a full understanding of fuel polishing systems for data centers, equipping you with the knowledge to maintain critical power readiness effectively. By the end of this module, you'll be able to design, check, operate, and maintain a fuel polishing system effectively. We'll start with understanding the readiness function, which ensures that stored diesel remains clean, dry, and filterable, especially critical for emergency generator starting. You'll learn how to trace the fuel flow from the underground storage tank, through pumps, filters, the ICM sample loop, and back to the return manifold. Next, we'll cover how to size turnover properly, calculating flow rates, tank turnover hours, and scheduling for multiple 110,000-liter storage tanks. You'll get a solid grasp on selecting the right filters and media, including staged particulate filtration, water separation and coalescing, and the importance of high-efficiency glass media ratings. You'll also learn to use controls and sensors by interpreting PLC and HMI data, understanding differential pressure alarms, flow monitoring, leak detection, and inline ISO cleanliness results. Maintenance planning is key, so we'll set practical differential pressure thresholds, verify cleanliness trends, and determine when cleaning or media replacement is necessary. Throughout the training, we emphasize readiness, repeatability, alarm response, and thorough documentation. Remember, while a polishing skid improves fuel condition, it doesn't replace the need for rigorous fuel procurement quality control, laboratory testing, or the maintenance mandated by NFPA and the owner. This comprehensive approach ensures your data center's fuel system stays reliable and in top condition. In this section, we're focusing on mission-critical fuel readiness and why fuel polishing is not just an optional extra. It's essential for ensuring emergency power availability. Stored diesel fuel naturally degrades over time while it's just sitting and waiting for an emergency. This degradation can cause fuel failures that don't become obvious until the generators are actually called upon to handle a real load, which is exactly when you need them most. To keep your fuel system ready, it's crucial to maintain cleanliness and dryness, ensure continuous circulation, and have clear evidence confirming the fuel's condition. Without these steps, you risk unexpected downtime during critical power events. This module will help you understand the importance of fuel polishing as a key strategy in keeping your data center's emergency power reliable and effective. Let's talk about why fuel polishing is essential for mission-critical readiness, especially in places like Indonesia, where biodiesel storage presents unique challenges. Emergency generators are only as dependable as the fuel supplied to them during a power outage. While engine-mounted filters provide a last line of defense, they can't handle cleaning up large volumes of contaminated fuel from bulk storage tanks. Biodiesel blends stored over time tend to collect water, sludge, acids, gums, rust, and microbial growth. This buildup can cause serious issues such as filter plugging and fuel starvation, which jeopardize generator performance. Active fuel polishing systems continuously clean the fuel, removing contaminants before they reach the generator's day tanks and sensitive components like strainers, injectors, and high-pressure common rail systems. For critical facilities like data centers, hospitals, and financial hubs, maintaining clean fuel isn't just about good housekeeping. It's a vital part of demonstrating emergency power system readiness. Regulations may not explicitly require installing fuel polishers, but the combined demands of fuel quality, environmental control, equipment protection, and business continuity planning make active fuel polishing a practical necessity in ensuring reliable operation when it matters most. In Indonesia, managing biodiesel fuel comes with unique challenges due to both the fuel composition and the tropical climate. The B35 and B40 biodiesel blends, which are important for national energy policy, require careful attention when it comes to storage. These blends contain FAME, or fatty acid methyl esters, which make the fuel more susceptible to water contamination, oxidation, and microbial growth if not properly controlled. Because Indonesia's tropical environment is characterized by high humidity, warm temperatures, and constant air exchange in storage tanks, condensation forms more readily. This condensation creates water at the bottom of fuel tanks, providing an ideal environment for microbes to grow at the fuel-water interface. Over time, this microbial activity can produce organic acids, gums, and sludge, which not only degrade the fuel quality, but also cause filters to clog and increase wear on high-pressure common rail systems. One critical risk with stored backup fuel is that tanks may appear full, but the fuel inside could be compromised, wet, oxidized, or biologically active, leading to potential generator trips or outright failure during an emergency. To mitigate these risks, contamination must be removed proactively before emergency use. Effective fuel polishing techniques include removing water from the tank bottom, staged particulate filtration, and using coalescers or water separators. Continuous inline cleanliness checks and trend logging help ensure the fuel remains ready and reliable. When designing fuel systems for these conditions, it's important not to size equipment based only on pump flow. You need to confirm the dirt-holding capacity of filters, water handling and drainage capabilities, and plan for regular runtime and sample testing to maintain long-term fuel quality and system reliability. This approach is essential for mission-critical operations in Indonesia's challenging biodiesel storage environment. Here we have the 4 essential pillars that define the mission-critical fuel polishing need. First, fuel polishing is fundamentally about reliability, compliance, asset protection, and cost control, all crucial for maintaining operational readiness. The first pillar is uptime protection. This means ensuring that emergency generators can perform without fail during a power outage by preventing issues like clogged filters, fuel starvation, unstable combustion, and injector damage. Next, regulatory and audit evidence is key. Fuel polishing supports all necessary documentation such as fuel quality testing, business continuity planning readiness, operations and maintenance logs, alarm reports, and maintenance records. These are vital for satisfying owners, authorities, and auditors alike. The third pillar is asset preservation. Fuel polishing helps protect important components like tanks, pumps, injectors, day tank strainers, and high-pressure common rail systems from harmful contaminants like water, sediment, corrosion, and abrasive particles. Finally, financial and environmental control is another major benefit. By reducing the need for bulk fuel disposal, emergency tank cleaning, downtime, contaminated waste handling, and costly emergency services, fuel polishing saves money and supports environmental responsibility. To sum it up, fuel polishing isn't just an optional add-on for critical backup power. It's a systematic, controlled maintenance process that transforms fuel condition into measurable, auditable readiness. Here we have a detailed regulation, standard, and audit map specifically for Indonesia, which is essential when designing and maintaining mission-critical facilities. This map serves as both a design review tool and a checklist for operations and maintenance evidence. Starting with the regulation side, Indonesia has mandated the use of B40 biodiesel blends starting in 2025. This means facilities must carefully manage stored fuel quality because higher biodiesel blends carry increased risks. To address this, facilities need compatible materials for B35 or B40, control water content in the fuel, maintain sample records, and track trends in fuel condition. Next, the financial sector, particularly banks regulated by OJK, must have disaster recovery plans in place. These plans require annual testing of critical infrastructure, including generators. Fuel readiness is monitored through detailed logs, records of fuel polishing runtime, alarm histories, and post-maintenance documentation to ensure reliability. Additionally, we have fire and safety standards like NFPA 110 and ASTM fuel testing methods, which provide frameworks for testing emergency power fuel quality. Labs should test fuel at least annually, checking for water, sediment, microbial contamination, stability, and particulate levels to maintain high fuel quality. The ISO 4406 standard addresses cleanliness in terms of particle counting, focusing on particles of certain sizes. This is monitored with inline cleanliness devices, setting target codes and alarm thresholds, and recording any required actions to maintain optimal fuel purity. Finally, environmental regulations require proper management of contaminated fuel, sludge, filters, and oily water as controlled waste. This involves containment systems, routing drainage to interceptors, maintaining spill logs, and producing waste manifests if needed. The practical takeaway here is that these laws and standards collectively enforce fuel quality, emergency power reliability, disaster recovery readiness, and environmental safeguards. The fuel polishing system plays a crucial role as the engineered solution that helps facilities prove compliance and maintain these crucial conditions over time. Here, we focus on how equipment datasheet benchmarks are vital inputs when validating the skid concept. These data sheets help us confirm critical aspects like flow rates, sensors, containment, controls, and maintainability. Looking at the mechanical side, we have examples like skid-mounted polishers and enclosed high-capacity polishers. When reviewing the design items, the flow range varies from about 100 to 600 liters per minute for smaller or medium packages, and up to 1,200 liters per minute for high-capacity packages, depending on the final setup. The pump philosophy typically involves a positive displacement, gear-type fuel circulation pump equipped with suction and outlet pressure gauges, plus a check valve for reliability. Filtration includes coarse inlet protection followed by coalescing or fine filtration, with selectable media ranging from 1 to 25 microns to meet cleanliness and water removal targets. Sensors play a critical role, including leak detectors, water sensors, differential pressure sensors, flow sensors, and suction and pressure gauges. These feed into controllers or building management systems to raise alarms and ensure smooth operation. Containment is designed to prevent leaks, featuring an integral basin or bund skid to catch any spills during maintenance or filter changeouts. The controller itself is local but quite advanced, providing scheduling, run status updates, alarm notifications, remote monitoring, and interlock capabilities to maintain safety and efficiency. One important caution is not to accept datasheet capacities at face value. Always validate actual flow considering factors like viscosity, suction lift, pipe friction, dirty filter differential pressure, return geometry, and whether multiple zones operate simultaneously. This ensures the system performs as expected in real-world conditions. Here, we're addressing why relying solely on standard generator filters isn't sufficient for protecting your engine. The filters located directly on the engine act as the final line of defense and are designed for maintaining normal cleanliness during operation. Their primary role is to protect the injectors, but they are not meant to clean the fuel tank itself. This means that if sludge or water from the bottom of the tank enters during an emergency start, these filters can quickly become clogged. When that happens, it can lead to low fuel pressure, reduced engine performance, or even a failure to accept load and a shutdown. That's where the fuel polishing loop comes into play. It operates before an emergency start by circulating fuel through a series of staged filters and water removal steps. This process removes contaminants such as sediment, rust, microbial growth, emulsified or free water, and oxidation products. Importantly, the system also logs runtime and cleanliness data, helping to track water levels, differential pressure, and alarms. In essence, the fuel polishing system serves as bulk tank contamination management, ensuring the fuel remains clean well before it reaches the engine filter. The key training takeaway here is not to wait for the emergency generator filter to become your first defense line. The tank itself must be maintained clean ahead of any outage to guarantee reliable generator performance. Let's dive into the operational controls necessary for ensuring mission-critical readiness of the fuel polishing system. It's not enough for the controller to just show that a pump ran. It must prove that the system actually cleaned the fuel. This distinction is crucial for maintaining fuel quality and system reliability. Looking at the operations table, we have several key functions, each with specific evidence or control purposes and typical instruments or data points used. For scheduled turnover, automatic polishing happens weekly or monthly, controlled by timers and monitored through runtime counters and totalized volume to ensure adequate treatment. Flow proof is about confirming that the commanded circulation actually occurred, which is verified by flow switches, low flow alarms, and pump feedback signals. This ensures that fuel is actively moving through the system. Water control is critical since water contamination can cause severe issues. Sensors detect water presence in coalescers or at the tank bottom, triggering alarms and logging water removal actions. Filter loading is monitored to detect restrictions before any bypass or damage happens. Differential pressure transmitters and switches, combined with baseline readings and warning or trip thresholds, provide this early detection. Leak containment stops the pump and triggers alarms before fuel escapes the skid containment area. This is managed with bund leak sensors, drain valve positions, and interceptor routing. Cleanliness confirmation measures and trends the particle count post-polishing, either with inline monitors or lab samples, to verify the fuel meets ISO cleanliness codes. Integration with building management systems or electrical power monitoring systems allows for comprehensive reporting of run status, faults, alarms, differential pressure, flow, cleanliness, water, and leak points, exposing the system's readiness to operations and management. As for the recommended operating philosophy, the system should only start when all permissives are healthy. It must stop immediately on conditions like leaks, very high differential pressure, no flow, or high water levels. Alarms are set for any abnormal trends, and operator acknowledgement along with maintenance closeout is required before resetting the system. This approach ensures safe, reliable, and effective operation every time. Here's an overview of the system based on the new input. We have 6 underground storage tanks, or USTs, each with a capacity of 110,000 liters, giving a total site storage of 660,000 liters for training purposes. These tanks are divided into 2 polishing zones, Zone A and Zone B. Zone A handles USTs 2 through 4, while Zone B manages USTs 5 through 7. Each zone polishes 3 tanks, alternating automatically under PLC and HMI control. Fuel polishing is designed to run as a scheduled readiness process, which means it operates independently from the generator's fuel consumption. The entire operation is monitored and controlled through an integrated human-machine interface, or HMI, that provides status updates on the USTs, polishing packages, distribution pumps, and overall system status. The polishing skid pulls fuel from a selected tank suction, passes it through filtration, and returns the polished fuel back to the tank or header. It's important to note that distribution pumps and day tank replenishment functions are separate, but they must be coordinated carefully with the polishing permissives and valve logic to ensure smooth operation. Finally, the controller records detailed data for each tank, including polished fuel volumes, particle counts, ISO cleanliness codes, and completion status, giving a comprehensive overview of the system's performance. This setup is part of the Data Center Fuel Polishing System Training Module 3. Here we see the UST zone arrangement and its readiness philosophy. The system is divided into 2 zones, Zone A and Zone B, each with 3 underground storage tanks of 110,000 liters capacity. This 2-zone setup allows us to maintain readiness in parallel, simplifying valve management and operation. In each zone, there is a dedicated polishing skid operating at around 156 liters per minute, which circulates and polishes the fuel in the tanks. After polishing, the fuel is filtered and then tested using the inline condition monitor, or ICM, to ensure quality. The key point is that each zone can be scheduled independently. For example, one tank gets polished and checked near the end of its cycle, while the next tank is prepared for polishing. This scheduling ensures continuous fuel readiness without disrupting the entire system. Additionally, a minimum polished volume target is set. This means a tank isn't considered fully serviced until enough fuel has circulated through the polishing skid, ensuring thorough cleaning. By running both zones in parallel, the system efficiently maintains all 6 tanks without requiring a single polishing skid to service every tank one after another. This approach increases operational flexibility and reduces downtime, ensuring that fuel quality and readiness are consistently upheld. Now let's dive into Section 2, where we'll explore the system architecture and process flow in detail. We'll start from the tank suction point, move through the various components and stages involved, and follow the fluid all the way to the filtered return. This includes understanding the key process logic and the multiple contamination control layers designed to maintain fuel quality. First, the process begins with selecting the appropriate underground storage tank, or UST, using inlet solenoids or isolation valves. These components ensure that fuel is drawn from the correct source without cross-contamination. Next, the gear pump circulates the fuel through a series of staged filters. These filters progressively remove contaminants to protect the fuel system and maintain optimum cleanliness. An inline cleanliness monitor is incorporated within a sample loop to constantly assess fuel quality. This monitor, along with the human-machine interface or HMI, logs the data for real-time tracking and record keeping. Finally, After filtration and monitoring, the clean fuel is returned to the correct tank or zone manifold, completing the circulation loop efficiently and safely. This overview sets the foundation for understanding how each part of the system contributes to fuel polishing and contamination control within the data center environment. Let's walk through the fuel polishing process flow shown here. This is a generic arrangement based on the operation and maintenance data, along with package specifications. We start with the selected underground storage tank suction point, where fuel is drawn into the system. Next, the fuel passes through an inlet solenoid valve combined with an isolation valve, allowing for controlled entry and the ability to isolate the system when needed. After that, it goes through a pre-filter or strainer, which removes larger debris to protect downstream components. Following this, the fuel reaches the gear pump equipped with a variable speed drive, or VSD, which helps regulate the flow and pressure to match system demand. The fuel then moves through the main particulate filter, crucial for removing fine particles that could harm the engine or equipment. Water removal is handled next by a water separator and coalescer, ensuring any moisture in the fuel is effectively separated to prevent corrosion or microbial growth. From there, the fuel is returned to the selected underground storage tank, completing the circulation loop. An important part of the system is the ICM sample loop, which takes a small, controlled sample of fuel, between 20 and 400 milliliters per minute, for analysis. This sample point is pressurized and located after filtration, so the fuel analyzed is representative and clean. The entire process is monitored and controlled by a PLC and HMI system, which includes isolation and alarms to ensure safe operation. There's also a bund or skid drip tray equipped with a leak detector and a normally closed drain valve that leads to a fuel oil interceptor. If a leak is detected, this setup triggers a safe shutdown and isolates the inlet and return valves to prevent spillage or contamination. Differential pressure sensors and gauges continuously monitor filter loading, while flow and pressure readings verify that the pump and control valve maintain proper circulation. Overall, this system ensures fuel is continuously cleaned, monitored, and safely handled to protect both equipment and the environment. When addressing contamination in fuel systems, it's crucial to control more than just visible dirt. The polishing process tackles multiple contamination modes to ensure system reliability. First, we have solid particles such as rust, dust, tank scale, and wear debris. These are managed using staged particulate media combined with ISO code monitoring, which helps maintain cleanliness standards. Next is free water, which can come from condensation, delivery water, or tank ingress. This type of water is controlled by water separators, drains, and water and fuel alarms to prevent damage. Emulsified water is a finer, dispersed form of water that can slip through simple strainers. Handling this requires specialized coalescing or water-absorbing media to effectively remove it. Microbial growth is another concern. Bacteria and fungi thrive at the fuel-water interface, producing sludge and acids that can deteriorate fuel quality. Preventing this involves maintaining dryness, regular sampling, and a proper treatment plan. Fuel degradation, caused by oxidation and the formation of polymeric gums, increases the risk of filter clogging. Managing this involves fuel turnover, lab testing, and an overall fuel management strategy. Lastly, air and vapor issues, often due to improper suction design, can lead to cavitation, low flow, and unstable sensor readings. These problems require the correct net positive suction head, or NPSH, and proper priming techniques. Overall, a comprehensive fuel management program integrates polishing with routine bottom water checks, fuel sampling, tank inspection, and corrective actions. Inline particle counters help monitor cleanliness in real time, but they don't replace thorough laboratory fuel property tests. This multi-layered approach ensures fuel integrity and system performance. Here, we're focusing on how the fuel polishing system helps reduce generator failure modes by preventing fuel-related faults before an emergency load situation arises. The key to this is understanding the various fuel risks and their consequences, and how we control these through multiple layers. For example, a high particle load can block engine filters and cause fuel starvation. To control this, we use staged filters along with differential pressure trend monitoring and ISO particle counters. If there's water in the tank, it can lead to injector corrosion and erratic combustion. We address this by using coalescers or water separators, regular draining, and water alarms. Loaded filter media can reduce polishing flow and risk bypassing filters, so we rely on differential pressure sensors with warning and maintenance thresholds. Wrong valve selection can cause fuel to flow incorrectly or return to the wrong tank, which we control with programmable logic controllers, solenoid feedback, and monitoring on the human-machine interface. Pump faults can cause no tank turnover or readiness issues, so duty and standby pump selection, variable speed drive fault detection, run hours monitoring, and flow feedback are critical controls. Finally, leaks or gasket failures can result in fuel spills or fire hazards. We manage this risk with containment structures like bunds and trays, leak sensors, automatic stop and close logic, and drainage to interceptors. The important takeaway is that failure prevention is a layered approach. Mechanical filtration, sensing instruments, alarm thresholds, isolation valves, and well-documented operator responses all work together to maintain fuel quality and system readiness. Remember, a tank can appear full but still be operationally unready if the fuel is contaminated, wet, or unable to pass through filters during an emergency demand. Now we'll move into Section 3, where we focus on the mechanical skid, pumps, filters, and containment aspects of the fuel polishing system. This section dives into the physical layout of the equipment, detailing the types of filter media used, how the pump circulation works, and the critical features for controlling leakage. The system uses a skid-mounted package that integrates the pump, filter housings, gauges, valves, and a controller into one compact unit. This design simplifies installation and maintenance. At the heart of this setup is a positive displacement gear pump, carefully sized to provide the necessary turnover rate to keep the fuel clean and in optimal condition. The filter train is arranged in stages to efficiently remove particles and water, ensuring the fuel quality meets the required standards. Additionally, there's a containment tray designed to manage any spills or leaks during maintenance or gasket failures, which is crucial for both safety and environmental protection. Overall, this section gives you a comprehensive understanding of how the mechanical components work together to maintain fuel quality in a data center environment. Here we have a real equipment visualization of a fuel polishing skid package, which is a typical skid-mounted assembly. This system includes several key components such as the pump, filters, gauges, local controls, and a containment base, all mounted together for efficient fuel treatment. Starting with the pump and motor base, this circulates fuel through the filtration loop. Gear pumps are commonly used because diesel fuel provides lubrication and positive displacement is necessary to maintain consistent flow in the loop. Next, the filter vessels play a crucial role. They contain particulate and water control elements housed vertically, with vents, drains, sample points, and differential pressure indicators to monitor filter performance. The pressure and differential pressure gauges are essential for operators. These field gauges and transmitters help compare the clean versus loaded filter pressure drop, enabling timely maintenance and ensuring the system runs smoothly. Local control is managed through a panel that includes switches, an emergency stop, and an HMI interface. This supports operators in controlling the system, performing maintenance, and acknowledging alarms quickly and safely. The bund skid base is designed for safety. It retains any leakage during maintenance or gasket failure, preventing environmental contamination by directing fuel to a controlled drainage system. Additionally, recommended skid details include features like a slope tray, a drain valve that remains normally closed and locked, removable grating, leak detection switches, corrosion-resistant coating, and easy lifting or maintenance access. It's also critical that the skid design keeps the electrical panel and instrumentation well protected from fuel exposure to ensure reliability and safety. Overall, this well-thought-out skid assembly is key to effective and safe fuel polishing operations. Let's talk about skid arrangement and maintainability, which are crucial for ensuring safe and efficient operation. A well-designed skid allows for filter replacement, drainage, and inspection to be done safely and consistently every time. Mechanically, we focus on creating a representative 3D process arrangement based on the technical input we've received. This helps us visualize the skid in an isometric view, making it easier to plan and understand the layout. Key design principles include maintaining straight runs and providing enough clearance to easily extract filter elements. High points should have vents to release trapped air, while low points must have drains to ensure proper drainage and safe media replacement. We also provide sample points both upstream and downstream of major filters to facilitate troubleshooting and system verification. Lastly, it's vital that the skid base is designed to retain any fuel that might be released during gasket removal or in the event of an unexpected seal leak. This helps contain spills and maintain a safe working environment. These considerations together enhance the maintainability and reliability of the fuel polishing system. Let's talk about the fuel gear pump used for circulation in our system. The key to selecting a positive displacement gear pump is ensuring it matches the required flow rate, fuel viscosity, suction lift, and the overall control philosophy of the system. Gear pumps are especially well suited for circulating diesel because they provide a stable flow even as pressure varies, and diesel fuel's natural lubricating properties help the pump operate efficiently. When choosing a pump, it's essential to size it for the worst-case scenario, meaning the lowest fuel temperature and highest viscosity you expect to encounter, plus any additional resistance from dirty filters. We have to confirm parameters like the net positive suction head, losses in suction piping and strainers, and ensure the pump can handle the maximum differential pressure. It's also very important to include relief protection so the pump doesn't deadhead against closed valves, which can cause damage. If the system requires variable flow or soft start capabilities, using a variable speed drive is beneficial. This allows you to adjust the pump speed and maintain precise flow control, often monitored and adjusted from the human-machine interface screen. Looking specifically at design checks, the pump must deliver the correct flow with some margin for dirty filters. We check cold diesel viscosity to understand required pump torque, ensure the pressure head is sufficient for filters, piping, and any sampling loops, and verify compatibility of seal materials with proper drip containment. To visualize the selection process, imagine a chart showing pump models across different flow rates, pressures, and viscosities. Selecting the right model means choosing one that fits within the operational envelope for your specific conditions. Overall, careful attention to these selection checkpoints helps guarantee reliable pump performance in the data center fuel polishing system. This slide focuses on the pump and variable speed drive, or VSD, flow control philosophy used in fuel polishing systems. The core idea here is to make the flow control predictable, which helps protect the filters from damage caused by excessive velocity or pressure. At the heart of this system, the operator uses the HMI, or human-machine interface, to set flow rate parameters in liters per minute, as well as minimum and maximum pump speeds. This input serves as the set point for the system. From the HMI set point, the PLC, the programmable logic controller, uses PID control logic to generate a speed command for the VSD. This command adjusts the gear pump flow, and the flow meter provides real-time feedback to the PLC. This creates a closed-loop feedback system that continuously monitors and adjusts flow to keep the operation within safe and efficient parameters. If the flow is too low, it may indicate problems like suction blockage, air entering the pump wear, a closed valve, or filter restriction. On the other hand, if pressure or differential pressure gets too high, the system will reduce or stall the operation and trigger an alarm to prevent filter bypass or damage. Finally, for each tank cycle, the controller tracks the total polished volume, ensuring the process is complete and effective. This comprehensive flow control approach helps maintain both system integrity and operational excellence. Here we have an overview of the filter train and media staging process. The key concept here is designing the filters in multiple stages, with each element fulfilling a specific role to ensure optimal performance. Starting with the mechanical stage, the filter elements are arranged vertically within the housing. Stage 1 uses a coarse pre-filter, which is essential for protecting the pump and removing larger debris from the fuel. This initial step helps prevent damage and ensures smoother operation downstream. Moving to Stage 2, we incorporate a fine particulate filter made from high-efficiency glass media. This stage significantly lowers the ISO cleanliness code, removing smaller particles to maintain fuel quality. Stage 3 focuses on water control, employing a combination of coalescers, separators, and water-absorbing media. Managing water content is critical as it helps prevent corrosion and microbial growth that could harm equipment. Finally, Stage 4 is the polishing or final filtration stage. It uses fine media to ensure the fuel is as clean as possible before it returns to the system or undergoes ICM sampling. A few design notes are important to consider. Differential pressure gauges or transmitters should be placed across each filter bank or the main train to monitor media loading effectively. When selecting filter media, factors like diesel compatibility, water removal strategy, particle removal efficiency, flow rate, viscosity, and allowable pressure drop must be balanced carefully. Additionally, when troubleshooting contamination, sampling both upstream and downstream of the filters helps determine if the issue originates from the tank or is due to filter bypass or carryover. This stage design approach ensures comprehensive fuel filtration and system protection. Let's talk about filter media efficiency and the beta ratio, which is a key concept in understanding how well a filter performs. The beta ratio essentially tells us how many particles enter the filter compared to how many actually pass through it. It's a measure of the filter's ability to capture contaminants. To put it simply, a higher beta ratio means better filtration. For example, a beta ratio of 2 means the filter captures 50% of particles at a certain size, while a beta ratio of 10 captures 90%, and it goes up from there. At very high values, like 4,000, the filter captures nearly 99.975% of particles. This data comes from actual manufacturer-supplied charts, which reflect mechanical media efficiency. However, it's critical to understand that a very high beta rating doesn't guarantee complete cleanliness in one pass. Factors like tank mixing, dead zones where fluid doesn't circulate well, and particle resuspension can all affect system cleanliness. So, beta ratio is just one part of the bigger picture. When selecting or sizing a filter, don't rely solely on the nominal micron rating. Instead, consider the beta ratio along with other important parameters like flow capacity, clean pressure drop, dirt holding capacity, water duty, and limits on bypass or filter collapse. This comprehensive approach ensures that the filtering system will perform optimally in your specific application. Water control is essential when managing fuel systems, as water acts both as a contaminant and a root cause for microbial sludge. To effectively manage water in fuel, we use a combination of mechanical techniques and alarms. First, tank bottom checks are critical. This means looking for free water at the bottom of tanks before it gets pulled into circulation, which helps prevent contamination early on. Next, we use coalescers or separators. These devices merge small water droplets together so they can be more easily separated from the fuel, improving water removal efficiency. Additionally, water-absorbing media play an important role. These materials trap fine water droplets where compatible with the system's flow and maintenance requirements, capturing water that might otherwise pass through. Water alarms are another key component. These alarms can be triggered by inline monitors or dedicated water and fuel sensors, providing early warnings so corrective action can be taken before problems escalate. Finally, a controlled drain procedure is necessary for safely removing water. This involves draining water to a waste or interceptor system with fuel handling controls to avoid environmental contamination. It's important to verify water removal through visual drain inspections, monitoring sensor trends, and periodic lab tests. Avoid draining water-fuel mixtures directly into the environment by using proper containment and oil-water separation procedures. After significant water removal, review microbial treatment strategies and check if filter elements need replacement to maintain system health. All these steps help ensure reliable fuel quality and protect the entire system from water-related issues. Maintaining the filter housing is crucial to ensuring that our fuel polishing system remains reliable over time. The quality of maintenance directly impacts system performance, so it's important to focus on several mechanical features that must be properly handled. First, vents located at the high point of the housing are used to remove trapped air before and after replacing filter elements, preventing airlocks that could compromise operation. Drains at the low point allow safe removal of fluids by directing them into a contained vessel or tray before opening the housing, minimizing spills and hazards. The differential pressure gauge or transmitter plays a key role by allowing us to record the clean differential pressure and monitor the loading trend, which helps in deciding when service is needed. Sample ports provide the ability to verify conditions upstream and downstream, which is vital for troubleshooting any issues quickly. When removing filter elements, it's essential to have sufficient vertical clearance to avoid damaging seals. Additionally, ensuring the correct gasket or seal material is used and inspecting it each time the housing is opened helps maintain a proper seal and prevents leaks. Finally, Isolation valves must provide positive isolation before maintenance begins and should be securely locked or tagged as required to ensure safety during service. Understanding and following these detailed maintainability requirements helps us keep our fuel polishing system running smoothly and reliably. Here, we focus on the concept of bund skid and leakage containment for pump and filter assemblies. The key idea is that the pump and filter must be installed on a skid designed to hold any leaks that may occur. This skid essentially acts as a containment area to prevent any fuel or fluid from escaping uncontrolled. The mechanical components mounted on the skid include the pump, filter housing, controller panel, and a bund drip tray or skid base. This base is sloped to direct any leaked fluid toward a drain sump. There's also a leak sensor to detect any unwanted fluid presence, coupled with a normally closed manual drain valve to control drainage. In terms of scenarios during maintenance, if the filter housing is opened or a gasket is removed, any residual diesel must remain inside the skid tray. If there is a fault, such as a leak from the gasket, pump seal, or a threaded joint during operation, the leak sensor will trigger an alarm and the PLC will stop the pump to prevent further leakage. Finally, if drainage is necessary, any fuel or water mixture is only released through a controlled valve that directs it to an approved collection system or interceptor. Importantly, all panel and electrical devices are either raised or separated to avoid contact with any retained fuel, ensuring safety and reliability in the system. Here we are looking at the skid containment sizing concept, which is crucial for ensuring safety during maintenance activities. The containment volume must be defined by considering the site-specific risks, local regulations, and the largest credible spill that could happen while performing maintenance. Mechanically speaking, the containment rules emphasize a minimum design basis that accounts for several factors: the drain-down volume from the filter housing, any residual volume in pumps and pipes, and potential leaks from gaskets before an automatic shutdown occurs. A practical and conservative approach is to calculate the retained volume of the largest open filter housing alongside any connected isolated piping, plus an additional freeboard to account for uncertainties. It's also important to implement level or leak detection systems before the containment overflows. The tray should be sloped toward a small sump to facilitate detection and controlled drainage. Do not route the skid drain directly to an interceptor without control. Always keep a normally closed valve and a maintenance procedure to manage potential spills safely. Looking at the table, for example, 2 filter housings at 35 liters each contribute 70 liters. Pipe and pump drain down is estimated at 25 liters, and gasket leaks before shutdown at another 78 liters. This gives a subtotal of 173 liters, with an additional 25% freeboard to cover uncertainties, bringing us to a recommended tray volume of at least 216 liters. Finally, keep in mind that this is a training example. The final bund volume must comply with all local environmental and fire safety requirements, as well as approved design criteria. This approach helps ensure both safety and regulatory compliance in data center fuel polishing systems. Now let's dive into Section 4, where we focus on the integration of PLCs, HMIs, controllers, and the Building Management System, or BMS. This part of the training explains how the polishing process is commanded, monitored, interlocked, and reported to ensure reliable operation. First, we use a redundant and industrial-grade PLC architecture. This means we have backup systems and robust hardware to prevent failures and maintain continuous control over the process. Next, a local human-machine interface, or HMI, allows operators to control polishing, schedule operations, and review tank results directly on-site. The HMI provides a user-friendly way to monitor and adjust the process in real time. Furthermore, the polishing system integrates seamlessly with the BMS and Distributed Control System, or DCS. This integration offers alarms and readiness status visibility at a higher supervisory level, ensuring any issues are promptly detected and addressed. Finally, controller-based interlocks are in place for critical components like pumps, valves, differential pressure, flow, and leak detection. These interlocks ensure the process operates safely by preventing potentially damaging conditions. This comprehensive integration makes the fuel polishing system efficient, safe, and transparent for operators and facility managers alike. Here, we have an overview of the control architecture for the polishing system. The polishing controller acts as the central coordinator, managing pumps, solenoids, instrumentation, and higher-level monitoring tasks. This ensures that all components work together seamlessly. Starting with the field devices, we have essential sensors like the flow meter, differential pressure sensor, leak switch, and valve feedback systems. These provide real-time data necessary for precise control. Local control is managed through PLCs or RIOs, variable speed drives, motor control centers with automatic transfer switches, and local HMIs. These elements handle the immediate control actions and feedback, ensuring the system operates efficiently on a day-to-day basis. On the supervision side, we have the fuel system HMI, building management or distributed control systems, trend logging, and maintenance report functions. These tools give operators a comprehensive view of system status and help with diagnostics and performance tracking. It's critical that automatic control relies on both command signals and proof signals, such as confirming valve positions, pump operation, VSD health, flow presence, and differential pressure within limits. Additionally, polishing commands must be inhibited if certain fault conditions occur, like leak alarms, excessively high pressure differentials, tank unavailability, incorrect valve states, emergency stops, MCC or VSD faults, or when local maintenance lockouts are active. Finally, readiness data should be accessible at both the local controller and higher-level facility monitoring systems, so operators always have visibility into system status and can intervene if necessary. This layered approach ensures safe, reliable, and efficient fuel polishing operations. Here we have a detailed look at the fuel polishing controller visualization, which is essential for understanding how the system operates in real time. These examples come from actual controllers and HMIs, but they've been anonymized to ensure the training remains vendor neutral. The controls include a local touchscreen panel designed similar to an emergency stop style controller, making it intuitive and easy to use. The polishing HMI provides a comprehensive overview, showing pump status, tank selection, flow rates, and a results table to monitor performance closely. Engineers have access to a settings pop-up, where they can adjust flow and variable speed drive limits to optimize system operation. The controller functions themselves are quite robust. They enable or disable polishing, schedule tank cycles, command inlet solenoids, start the selected pump, regulate flow, and log all results for accurate tracking. From the operator's perspective, the interface clearly displays key statuses such as active, healthy, or alarm conditions, while also indicating the selected tank, flow rate, pump speed, valve status, differential pressure, leak status, and ICM results, ensuring full visibility at a glance. Maintenance mode is designed with safety in mind. It isolates the skid, prevents any unintended automatic starts, and guides technicians step by step through safe procedures for draining and replacing filters. This careful design helps maintain both safety and system reliability throughout maintenance activities. On this slide, we focus on the HMI polishing overview, specifically what the operator sees and how it guides their actions. The HMI serves as the main readiness screen, showing the current status of the polishing system and cleanliness results in real time. First, the status indicators are crucial. They tell us if the system is active, running smoothly, or if there's an alarm signaling a fault. These indicators help the operator quickly assess the system's health at a glance. Next, the command buttons available, such as Enable, Pump Start, Interlock, and Settings, are protected by user level and operating mode to ensure only authorized personnel can make critical changes. The tank result table displays detailed polishing data for each underground storage tank, including polished volume, ISO cleanliness codes, particle counts, and completion status. This provides a clear view of how effectively the polishing process is proceeding. Flow reading is another important element. The flow feedback lets the operator confirm that the circulation loop is running at the intended rate. If flow is low or stops, an alarm will notify, and the system should shut down to prevent damage. Operators are encouraged to ask themselves key questions each shift. Are the correct tanks enabled? Is the pump functioning properly? Is the flow rate being achieved? Are filter differential pressures within acceptable limits? And finally, is the latest ISO cleanliness result within the target range? Importantly, the HMI is much more than just a visual schematic or drawing. It's a dynamic readiness dashboard that provides essential, actionable information to keep the fuel polishing system running safely and effectively. Here, we see the automatic polishing sequence as captured from the operation and maintenance logic. The process starts with the controller selecting one underground storage tank, or UST, to polish. Near the end of polishing, the system obtains a cleanliness result before moving to the next tank. Let's break down the controls involved. First, the PLC selects the next eligible tank by evaluating factors like whether the tank is enabled, its minimum fuel volume, its priority status, and whether it has been recently completed. Next, the system opens the necessary valves. This means the selected inlet and return solenoids, along with any manual isolations, must be confirmed open. Any incorrect valve states are interlocked to prevent errors. Once the valves are confirmed, the duty pump starts through the motor control center or variable speed drive. The system then verifies flow and pressure to ensure proper circulation. During polishing, the controller keeps track of the polished volume against a daily or cycle target. This way, it ensures that each tank receives the correct treatment volume or time. As polishing nears completion, the Inline Cleanliness Monitor, or ICM, conducts a test to measure particle cleanliness. This test typically takes about 2 minutes and occurs near the end of the polishing period. After the test, the HMI stores the results, including ISO cleanliness codes and particle counts. If the tank meets the set criteria, it is marked complete in the system before the controller moves to the next tank. This sequence ensures a thorough and automated polishing process, maintaining fuel cleanliness efficiently across multiple tanks. Let's take a closer look at the UST scheduling, volume totalizing, and the result table. Each underground storage tank, or UST, must have proof of both circulation and cleanliness to ensure proper maintenance and fuel quality. The controls include an HMI table that displays polishing results for each UST individually. This table shows key parameters like flow rate, polishing time, interval or delay between tanks, polished volume, and cleanliness indicators such as ISO codes and particle counts. These values are critical because they guide the pump and variable speed drive targets, define how long a tank is polished, the wait time before switching tanks, and provide evidence that the fuel meets cleanliness standards. When it comes to scheduling logic, there are a few important rules. First, a minimum polished volume must be set for each UST, and the tank won't be marked complete until this daily or cycle target is achieved. Second, a delay between tanks is necessary. This helps valves settle, prevents transient issues, and ensures the interlocks function correctly. Third, if a tank is disabled, has low fuel levels, triggers an alarm, or becomes unavailable, the PLC will skip that tank and log the reason. Lastly, it's important that the integrated control module's results are attributed to the specific tank being polished, rather than a general system status, so accountability and accuracy are maintained. In summary, this system ensures that each UST undergoes thorough polishing with clear verification of fuel circulation and cleanliness, supported by precise scheduling and control logic for optimal performance. Here we're looking at the pump selection and isolation valve logic, which is critical for ensuring safe and efficient operation. The system employs active pump selection, combined with isolation valves and solenoid valve proving, to manage the pumps effectively. Only the pump that's been actively selected should be able to start automatically. Any pumps not selected stay off and isolated to prevent any unintended operation. When choosing which pump to run, the system considers factors like the total running hours, maintenance status, and any fault history. This helps balance pump usage and ensures reliability. The manual isolation valve for the active pump must be open for operation, while the valves on inactive branches should remain closed, except if the system is set up for standby mode. The solenoid valve logic is designed to stop polishing fluid from passing through 2 tanks simultaneously unless the system's hydraulic design explicitly allows for that. If the active pump fails, the controller will raise an alarm and can switch to standby, but only once all valve positions and operational permissives are correctly aligned to ensure safe transfer. In terms of training, before any maintenance work, it's essential to confirm the pump cannot auto-start and that all isolation valves are positively closed. After changing over a pump, flow rates and differential pressure trends should be checked to ensure they've returned to expected values. This training ensures safety and system reliability during operation and maintenance. Here we have an overview of the PLC and remote I/O topology used in industrial control systems. The key point here is the implementation of a redundant and industrial control architecture, which significantly enhances both visibility into system operations and overall resilience against failures. Looking at the design implications, the control panel typically supplies 230 volts AC for control power and 24 volts DC for instrumentation power. For critical fuel functions, motor control centers receive dual power paths through an automatic transfer switch, ensuring continuous operation even if one power source fails. Segmenting the PLC and remote I/O is crucial. This segmentation allows any field failures to be quickly diagnosed and maintained without affecting the entire system. Additionally, it's important that networked human-machine interface or building management system points are not the sole method for ensuring local safe operation. Hard interlocks or fail-safe mechanisms must be implemented for emergency stops, leaks, high differential pressure alarms, and critical valve states to guarantee safety and proper shutdown when necessary. The table summarizes the typical signals handled at each control layer. PLCs manage sequencing, interlocks, timers, and valve commands. Remote I/O units handle local digital and analog inputs and outputs close to the skids and tank headers. Variable speed drives and motor control centers monitor run status, faults, speed, current, and start/stop commands. HMIs provide operator control commands, status updates, and settings feedback, while building management systems or distributed control systems track readiness alarms, trends, and summary points. This structured approach ensures a robust and maintainable control system, which is vital for complex operations like data center fuel polishing systems. Here, we focus on the critical data points recommended for PLC, HMI, and BMS or DCS systems in managing fuel polishing operations. These data points are essential not only for day-to-day operation, but also to provide evidence of readiness, ensuring the system is always prepared when needed. Under controls, we have specific points to monitor. For example, the polishing enable or command signals allow us to start or inhibit the automatic polishing process directly from digital inputs or outputs, including HMI commands. Monitoring the pump status, whether it's running, faulted, or its speed, helps verify circulation and quickly identify any failures that could disrupt the process. Flow rate and totalized volume readings are crucial because they prove water turnover and help schedule when the polishing should be complete. Filter differential pressure measurements alert us to media clogging or the need to replace filters before the system's efficiency drops. Detecting water contamination in fuel is vital. We're looking for that via digital and analog inputs, which can trigger necessary maintenance actions like draining. Measuring particle count or ISO cleanliness codes through communications or analog signals informs us about the fuel's cleanliness level in specific tanks. Valve commands and feedback prevent incorrect tank flow or deadheading that could damage the system. Leak detection is critical. It must immediately halt pumps, close valves, and trigger alarms to prevent spills or system damage. We also monitor incoming power and automatic transfer switch status to confirm electrical availability, ensuring the fuel system is always ready. Finally, maintenance mode allows operators to lock out automatic functions during servicing, protecting both personnel and equipment. At the BMS or DCS level, summary readiness status and high-priority alarms should be displayed for quick situational awareness, but detailed settings must be kept accessible only to authorized personnel via the HMI or PLC. Trend data for key parameters like flow, differential pressure, specific tank statuses, totalized volume, cleanliness codes, water alarms, pump speed, and faults should be recorded to provide clear insights into system performance over time. This comprehensive monitoring and control approach supports both operational reliability and regulatory compliance. Let's go through the alarm and interlock philosophy that guides our system control. The fundamental principle here is that every automatic action taken by the system must ensure safety first and provide a clear, understandable message to the operator. This way, operators always know what's happening and what action to take if needed. Looking at the controls table, we see various conditions, how they're detected, what the controller does in response, and what the operator should do. For example, if a leak is detected via a leak switch or level sensor in the skid tray, the controller will stop the pump, close solenoid valves, and trigger an alarm. Then, the operator must inspect the source of the leak, follow the draining procedure, and repair the gasket or seal. Similarly, If there's a high differential pressure across the filter detected by a DP transmitter, the system first issues a warning and then stops at a critical high level. The operator's role here is to replace or clean the filter media and record the new clean differential pressure. Low or no flow situations are managed by stopping the pump after a delay and sounding an alarm, prompting operators to check key components like valves, suction lines, pumps, filters, and air locks. When cleanliness levels in the ICM are too high, indicated by ISO or particle results, an alarm sounds and the tank is flagged as not clean. The operator should continue polishing, send samples to the lab, and investigate the contamination source. Water alarms from the ICM or water sensors also trigger alarms and maintenance flags, signaling operators to drain water, inspect the tank, and replace water media if necessary. Incorrect valve feedback is caught by limit switch or proof signals which inhibit startup until valve alignment and actuator status are verified. Finally, faults in the variable speed drive or motor control center, detected through system feedback, cause the stop sequence and alarm, requiring troubleshooting of power supply, motor, drive, or overload issues. It's crucial to set alarm priorities based on the consequence of each condition. High-priority protections include leaks, critical high differential pressure, emergency stops, and wrong valve feedback. These ensure that the most dangerous or impactful faults are addressed immediately to maintain system safety and reliability. Here we have a sensor map designed for a complete polishing skid, which serves as an essential tool during the design review process. This map acts like a checklist, ensuring all critical controls are accounted for and properly integrated. Starting with the controls, key components include the upstream sampling tank, or UST, inlet and return valves, pump, filters, and the ICM sample point. Monitoring these components is crucial for the system's reliable operation. We also track several important measurements through various sensors. Tank level sensors using LSH and LEL indicators, valve position feedback confirming open or closed status, suction and discharge pressure via pit sensors, as well as flow and totalized flow with fit sensors. Differential pressure across filters is monitored using DPT sensors to detect filter loading conditions. Particle contamination and water content levels are identified through ISO codes, providing insight into fuel quality. Additionally, a leak switch on the tray sump serves as a critical discrete alarm to detect any leaks promptly. The motor control center and variable speed drive provide real-time run status, fault alerts, and speed information for the pump. This feedback is essential for maintaining performance and addressing issues proactively. We recommend continuously trending key analog signals such as flow, differential pressure, overall pressure, tank levels, and pump speed or current to identify anomalies early. Likewise, essential discrete alarms should include leak detection, high differential pressure triggers, pump faults, valve mismatches, emergency stops, power unavailability, and ICM faults. Using this sensor map as a design checklist helps ensure comprehensive monitoring and control of the fuel polishing system, ultimately safeguarding operational efficiency and fuel integrity. Now we're moving into Section 5, where we'll dive into sensors, inline cleanliness, and ISO standards. This section focuses on how fuel cleanliness is measured, interpreted, trended, and ultimately used to make informed maintenance decisions. We'll cover inline contamination monitors that track particle levels according to ISO, NAS, and SAE codes, ensuring we meet strict cleanliness requirements. We'll also discuss differential pressure monitoring, which helps us understand filter media loading and when filters need attention. Additionally, water and temperature alarms, as well as sample loop installations, play a crucial role in detecting contaminants early. Throughout this section, we'll reference important standards and highlight mission-critical cleanliness targets that keep your data center fuel system running smoothly and reliably. Here we have an overview of the inline contamination monitor workflow. The monitor works by converting a controlled sample flow into a cleanliness code and alarms to keep us informed of fluid quality in real time. First, a pressurized sample is taken after filtration. It's important to ensure the sample is representative by avoiding any air bubbles or excessive restrictions that could skew the results. Next, the flow is carefully controlled, ideally near 200 milliliters per minute, although this target can vary depending on the equipment used. The core of the process involves optical counting. The ICM uses an LED light extinction sensor to count particles in different size channels, such as those greater than 4, 6, and 14 micrometers. This allows precise measurement of contamination levels. Following particle detection, the system classifies the data and reports an ISO 4406 cleanliness code, with optional classifications like NAS or SAE. Finally, the results, trends, and alarms are logged and stored in the PLC or HMI. When cleanliness limits are exceeded, the system triggers alarms to prompt action. As a best practice, we use the ICM primarily to monitor trends and overall readiness. Any unusual readings should be verified through traditional sampling and lab analysis. Alarm settings for cleanliness, water content, and temperature can be customized, and alarm responses should be integrated with the PLC for effective management. This approach ensures continuous and proactive fluid cleanliness monitoring within the fuel polishing system. Here, we have a real picture of the Fuel Polishing Cleanliness Monitor, or ICM for short. One crucial point to understand is that the ICM needs a stable sample pressure and flow to provide accurate cleanliness results. Without this stability, the readings could be unreliable. Looking at the installation, you can see the inline monitor paired with a pressure gauge. This pressure reference is essential because it confirms that the sample loop is actively being fed during the polishing process. Typically, a manual needle or control valve is used to adjust the sample flow to fall within the required range. It's also critical that the sample line is properly flushed, free of leaks, and routed to avoid trapped air. Any air in the line can disrupt the sample quality and lead to false readings. Additionally, the operator must always check the ICM status and health before trusting the ISO cleanliness code displayed. The monitor's status LEDs and keypad visualization provide real-time feedback, making it easier to interpret data and respond quickly if issues arise. There is also an alarm level setting concept in place to alert operators when cleanliness parameters fall outside acceptable limits. Finally, a key training reminder. Particle counter results can be misleading if the sample loop isn't set up correctly. Problems like trapped air, insufficient flow, unflushed hoses, stagnant fuel, or incorrect connection points can all affect the accuracy of the readings. Proper training and careful maintenance are therefore essential for reliable fuel polishing results. Here we have the key technical data for the Inline Contamination Monitor, or ICM. This device uses a highly precise LED light extinction method to automatically analyze particles in a fluid. It can detect particles across multiple size channels, ranging from greater than 4 micrometers up to over 70 micrometers, which helps ensure detailed cleanliness assessment. The cleanliness results are reported using widely recognized standards like ISO 4406, NAS 1638, and SAS 4059, depending on the setup. The ISO cleanliness codes can range from 0 to 25, with the device typically achieving an accuracy of plus or minus half an ISO code at the main particle channels. This gives us confidence in the reliability of the data it produces. Testing time is fully configurable, usually set around 120 seconds in typical factory settings, but it can be adjusted anywhere from 10 seconds to an hour based on the need. Sample flow rates are flexible as well, ideally maintained around 200 milliliters per minute, but can vary between 20 to 400 milliliters per minute. Regarding inputs and outputs, the ICM supports switched digital in and outputs, serial communication, and analog options, which depend on the particular configuration installed. It also has robust data storage capability, saving thousands of time-stamped results to track contamination trends over time. Power supply for the unit is low-voltage DC, so it's critical to verify wiring documents thoroughly before making any connections to ensure safety and proper operation. Always remember, when commissioning the ICM, to verify parameters like sample flow and pressure, ensure proper drain and return lines, check alarm wiring, confirm communication mapping, and scale HMI tags correctly. Do not energize or wire any outputs until the wiring diagram and voltage ratings have been fully approved. This comprehensive approach ensures the ICM operates reliably, providing accurate contamination monitoring that's vital for maintaining fuel polishing system cleanliness and overall equipment health. When it comes to fuel cleanliness monitoring, it's important to use multiple methods because each one answers a different question. Let's look at some key options and what makes them useful. Inline particle monitors provide continuous, automatic trending for each tank. This is great for real-time readiness dashboards and alarms, but they require correct sample flow and don't give a full picture of fuel properties. Portable particle counters are excellent for independent field verification. They're handy for troubleshooting and spot checks, although they involve manual sampling and need a trained technician to operate. Laboratory analysis offers a comprehensive assessment of fuel quality, including water content, microbes, oxidation, and other properties. While it's more thorough and used for compliance and root cause analysis, it's slower and done periodically rather than continuously. Differential pressure trend monitoring directly indicates filter loading, helping trigger maintenance, but it doesn't identify the type of contamination on its own. Lastly, tank bottom water checks help find free water right at the source. This method is manual and depends on location, but is essential for planning drain and inspection activities. For mission-critical readiness, the best approach combines inline monitoring for early warning with periodic lab testing to confirm the fuel remains within specifications. Remember, one good sample doesn't prove a tank is clean if sludge or water zones haven't been properly circulated and checked. Let's talk about the ISO 4406 Cleanliness Code and how to read it. This standard uses 3 code numbers that correspond to particle counts at sizes of 4 micrometers, 6 micrometers, and 14 micrometers. These 3 numbers provide insight into different ranges of contamination. The first number, representing particles equal to or larger than 4 micrometers, indicates very fine particles and gives a general sense of the overall contamination trend. The second number, for particles 6 micrometers and above, reflects fine particles that are crucial because they can affect fuel system wear and filterability. The third number corresponds to larger particles, 14 micrometers and larger, which are strongly associated with filter clogging. The code scale works by doubling the particle count with each one-step increase. For instance, an example code like 18/16/13 tells us the amount of contamination at each particle size. A key point to remember is that a lower ISO code means cleaner fuel. Each step down roughly halves the number of particles in that size range. It's essential that both inline monitors and lab results use the same cleanliness standard and calibration basis for accurate trend comparisons. Finally, the target for fuel polishing should align with the engine owner's requirements. In this training, the example clean target we've used is an 18/16/13 code. Understanding these codes will help you maintain effective cleanliness levels throughout your fuel system. When managing mission-critical fuel, it's essential to have clear standards and cleanliness targets. These standards serve as a framework, but the final acceptance must always align with the owner's specifications and the engine or OEM requirements. Cleanliness is a key focus because impurities or contaminants can lead to equipment failure or decreased reliability. Let's look at some critical frameworks and how they guide fuel quality and cleanliness. First, the ESDM or local fuel specifications ensure that fuel supplied and stored within Indonesia complies with national requirements and the current biodiesel blend program. Evidence like supplier certificates of quality, delivery logs, and compatibility reviews for blends such as B35 or B40 confirm adherence. Next, ASTM D975 provides standardized tests for diesel fuel, measuring properties like water and sediment levels, viscosity, sulfur content, flash point, cetane number, and degradation indicators. Among these, water and sediment content is often the most emphasized parameter because excess amounts compromise fuel stability and performance. We rely on lab test results to verify these criteria. NFPA 110 sets standards for emergency and standby power fuel quality, requiring at least annual testing using ASTM methods or as recommended by the engine OEM. This includes bottom sampling to check for contaminants, with records maintained for any corrective actions taken. ISO 4406 addresses particle cleanliness through a coding system that counts particles at different sizes. For mission-critical systems, a typical target is ISO 18/16/13 or better, but this should be refined based on manufacturer and project-specific requirements. OEM and high-pressure common rail engine requirements are stringent because modern engines have very tight injector clearances and operate at high fuel pressures, making them highly sensitive to water and particle contamination. Following OEM limits ensures engine longevity and warranty compliance. Finally, environmental and safety regulations mandate that any oily water, sludge, spent filters, or contaminated fuel must be properly contained, drained, labeled, and disposed of according to approved procedures. Proper infrastructure like bund skids and leak sensors help manage these risks effectively. As a recommended training target, stored generator fuel should maintain a cleanliness level of ISO 18/16/13 or better, be dry and bright, stable, low in water and sediment, and verified through inline monitoring combined with periodic laboratory sampling. This comprehensive approach ensures that mission-critical fuels meet the highest standards for performance, safety, and environmental compliance. Let's talk about the key requirements for installing the ICM hydraulic system to ensure accurate cleanliness data. First and foremost, it's important to understand that reliable cleanliness readings depend largely on the sample loop, not just the sensor itself. This means that how you set up the sample collection path can have a big impact on the data quality. When connecting the hydraulic system, make sure to tap into a representative pressurized stream. Avoid any dead legs or stagnant areas in the sample lines, as these can trap air and give misleading results. The sample control valve should be adjusted to provide a stable flow to the monitor. Keep in mind that very clean fuels might actually require longer testing times or a higher sample flow to get accurate readings. The return or drain line is just as important. It needs to be unrestricted and routed in a way that prevents back pressure, spills, or any indication of low flow that isn't real. After any maintenance work, always flush the sample tubing thoroughly before taking the first measurement to avoid contamination. Overall, keeping these installation practices in mind will help you achieve reliable, consistent cleanliness data, which is critical for monitoring and maintaining fuel quality in your system. Here, we're focusing on the critical aspects of integrating the ICM electrical system with the PLC. Integration starts with ensuring the controller includes power connections, start inputs, communication for results, and alarm outputs. Cleanliness is also a vital consideration to maintain system reliability. Looking at the integration details, we first verify the power supply for low-voltage DC range, correct polarity, proper fusing, and adequate panel capacity. The start or trigger signal is often controlled by the PLC, which may initiate a test near the end of the polishing cycle to ensure timely operation. Alarm outputs play an important role by mapping cleanliness, water levels, and temperature alarms to the PLC's priority system, allowing for immediate response if any parameters fall outside acceptable limits. Communication integration involves mapping ISO codes, particle counts, water and temperature data, test status, and fault status to ensure comprehensive monitoring. Proper shielding and grounding are crucial to reduce electrical noise. Following the wiring guide, it's important to separate signal wiring from noisy sources like variable speed drives or motor power cables. Finally, defining the fail-safe state is essential. If the ICM goes offline, the system must be configured to either continue polishing while marking the result as invalid or to stop the process entirely, depending on the owner's operational rules. This ensures safety and reliability within the fuel polishing system. Here, we're focusing on the differential pressure sensor and its role in monitoring filter cleanliness. Differential pressure, or DP, is a key measurement indicating how much the filter media is loading up with contaminants and whether it might need cleaning or replacement. Essentially, DP is calculated as the difference between the pressure at the filter inlet and the pressure at the filter outlet, which directly tells us how clogged the filter has become. We track this pressure difference against several threshold levels. When the filter is clean, we record a baseline delta P at a known flow and temperature. As the filter starts to load, we enter the warning stage, where the trend of rising DP signals that inspection and scheduling maintenance is needed. If the DP surpasses a set maintenance threshold, meaning the filter is too loaded, we replace or clean the media. At the high or trip level, the system must stop polishing fuel to avoid bypass, filter collapse, or unsafe pressure conditions. It's important to configure these thresholds carefully, staying below manufacturer limits for bypass or element collapse. Temperature also plays a critical role because cold fuel increases viscosity, which raises the clean delta P. So, we must always compare DP readings at similar flow rates and temperatures, or apply corrections if conditions vary. On the flip side, a sudden drop in DP might indicate a problem like a ruptured filter element, an open bypass, or even sensor line failure. After maintenance, the baseline must only be reset once a leak check, proper venting, and stable flow tests confirm that the system is operating correctly again. This structured monitoring ensures that the fuel polishing system runs safely and efficiently with well-maintained filters. Here we have an example of using differential pressure thresholds for maintenance planning. Instead of reacting to just a single alarm number, it's important to use clean baseline trending. This means tracking the pressure difference relative to a clean, baseline state over time, which helps identify early signs of filter loading. Look at the trend example here, showing how cleanliness gradually shifts from a clean element toward maintenance and even high alarm levels. The table breaks down these bands clearly. When in the normal band, the system is near the clean baseline. Just record the value and continue regular polishing. Once a warning band is reached, you should start planning a filter change and check for any water or particle issues. When you hit the maintenance band, flow control becomes difficult or the differential pressure exceeds the threshold. At this stage, the filter media needs to be replaced or cleaned at the next safe opportunity. Finally, if the high band is triggered, it means the protection limit is reached. The pump must be stopped immediately, the system isolated, and a thorough investigation conducted. Under no circumstances should you bypass this alarm. To effectively manage these thresholds, the recommended controller fields should include the current DP, clean baseline DP, warning, maintenance, and high thresholds, as well as the date of the last element change and operator acknowledgement. This structured approach ensures timely maintenance and prevents system failures due to clogged filters. Let's walk through the filter cleaning and media replacement decision tree. When deciding on maintenance actions, it's important to look at several factors together: differential pressure, cleanliness results, water conditions, and visual inspection. We start by asking if the polishing system is running. Next, check if the differential pressure is above the warning threshold. Then look for any ISO or water alarms. If the flow rate is below the set point, that's another red flag. Depending on these observations, different maintenance steps are recommended. For example, if the differential pressure is high, but the ISO cleanliness is improving, this usually means the media is loading normally, so schedule a replacement of the element. If the differential pressure is high and there's a water alarm, you should drain the water, replace the water media or coalescer, and inspect the tank bottom for any contamination. In cases where the differential pressure is low but the ISO cleanliness is poor, this could indicate issues like the wrong sampling point, bypassing, a ruptured element, poor mixing, or sludge resuspension in the tank. When flow is low combined with low suction pressure, it's essential to check the suction valve, strainer, air ingress, or possibly a low fuel level. And if flow is low but differential pressure is high, this points to a plugged filter. So stop the operation before reaching the bypass or collapse limit. After replacing filter media, remember to vent the system, check for leaks, record the clean differential pressure, and run a verification polish to ensure everything is functioning correctly. Together, these steps help keep the fuel polishing system running efficiently and maintain fuel quality. Here we focus on leak detection and the corresponding safe shutdown response. The key point is that the containment skid must be integrated into the controller alarm logic to ensure a coordinated and effective reaction to any leaks. First, cleanliness is critical, especially around the skid base and potential leak points in the equipment. When a leak is detected and the leak switch is activated, the system triggers an alarm within the PLC, which then latches to hold the alert state. Once the alarm is latched, the controller initiates a safe shutdown sequence. This includes stopping the pump or variable speed drive, closing the inlet and return valves to isolate the leak, and notifying the human-machine interface, as well as the building management or distributed control systems. Following notification, the system proceeds to a controlled cleanup process to safely manage any leaked fuel or contaminants. A crucial controller response is that the leak alarm must not be treated as just a warning. Instead, circulation should stop immediately before any fuel can reach tray overflow or cause electrical hazards. Operators should not drain the tray until they have confirmed the leak source has been isolated and there is a proper receiving container or interceptor route available. After any repairs, resetting the alarm and system should only happen after thorough inspection, replacement of gaskets or seals if needed, conducting a leak test, and receiving a housekeeping sign-off. It's also important to monitor and trend small, recurrent leaks carefully. Multiple instances of gasket seepage may indicate problems like incorrect installation torque, unsuitable gasket material, or excessive vibration. One critical training point to remember is that the bund skid protects the facility effectively only when the drain valve remains normally closed and the leak signal is wired to automatically shut down the system. This ensures leaks are managed promptly and safely every time. Now, in Section 6, we will focus on sizing calculations and turnover examples specifically for 6 underground storage tanks, each with a capacity of 110,000 liters. I'll walk you through how to calculate the circulation flow, polishing duration, and filter capacity for these tanks. We'll start by reviewing the tank turnover formula, which is essential for understanding how fuel cycles through the system. Then, we'll explore the Zone A and Zone B parallel calculations, which help us optimize the flow distribution between different zones. We'll also interpret flow rates of 156 liters per minute and 312 liters per minute to understand their practical implications in the system. Finally, we'll look at an example involving filter capacity, the beta ratio, and the cleanliness target. This will give you a clear picture of how to ensure your filters are correctly sized to meet fuel quality standards during polishing. This section is critical for designing and maintaining an efficient fuel polishing system in data centers. Let's dive into the core sizing formulas for fuel polishing systems. The process begins with determining the required turnover, which is essentially how often the entire volume of fuel should be circulated through the system. The key formula for required flow rate is Q equals volume times safety factor divided by turnover time in minutes. This tells us the flow rate needed to achieve that turnover within the desired time frame. Turnover time itself is calculated by rearranging this formula. It's the volume times safety factor divided by the flow rate, again converted into hours. When planning for multiple turnovers, for thorough cleanup, runtime is calculated by multiplying the number of turnovers by the volume, then dividing by flow rate and converting to hours. It's important to pay attention to the design allowance or safety factor, typically between 1.2 and 1.25, to ensure a margin of safety without overestimating pump capability. The number of turnovers, represented by N, usually exceeds 1 and depends on cleanliness targets. However, sizing doesn't stop at pump flow calculations. You need to verify the actual pump curve under real conditions, considering fuel viscosity variations, suction lift, and filter differential pressure when dirty. Check suction velocity. Ensure you have adequate MPSH margin to avoid cavitation. Watch for vapor or air ingestion risks, and set appropriate low-flow alarms. Filter capacity is critical too. Both dirt holding and water removal must be confirmed so filters can perform effectively. Also, consider pipe size, valve pressure drop, and how return lines and tank mixing zones might impact flow. If you're dealing with multiple zones and pumps in parallel, make sure the equipment is rated accordingly. A quick rule of thumb is that tank volume divided by 1,000 approximates the flow rate in liters per minute needed for about 1 turnover in 16.7 hours, before adding a safety factor. With a safety factor of 1.2, this gives you around a 20-hour turnover window for planning. Finally, remember that turnover measures circulation, not cleanliness directly. Always use ISO cleanliness trends, water content results, and differential pressure trends as evidence that polishing is effective. This comprehensive approach ensures your fuel polishing system is properly sized and performs reliably to maintain fuel quality. Here we have a detailed sizing example for underground storage tanks and polishing zones at a data center fuel polishing system. The setup includes 6 underground storage tanks, each holding 110,000 liters, split into 2 zones. Zone A with tanks 2 to 4 and Zone B with tanks 5 to 7, each totaling 330,000 liters. The design incorporates a safety factor of 1.2 to ensure adequate planning and reliability. Looking at flow requirements, the existing example shows a flow of 156 liters per minute per zone, which translates to about 14.1 hours with the safety factor for a 110,000 liter tank, and about 42.3 hours for a full 330,000 liter zone. This is suitable for weekly or low-risk maintenance cycles, but insufficient for a full 24-hour turnover. If 2 parallel or dual-stream systems operate simultaneously at 312 liters per minute, then a 24-hour turnover per zone is achievable with the safety factor. However, it's crucial to emphasize that this flow rate can only be considered valid if both pump streams are truly operating in parallel, and the entire system, including filters, piping, controllers, and power supply, is rated for this combined operation. For mission-critical data centers, the recommendation is to design each 330,000-liter zone to complete at least one turnover within the owner's specified window. Specifically, for a 24-hour high-readiness target with the safety factor of 1.2 applied, a flow rate of about 275 liters per minute per zone is advised. Operating both zones together would then yield a total site flow of approximately 550 liters per minute. Faster turnover times, like 12 or 8 hours, require even higher flow rates and bring additional considerations, such as checking filter vessel and pipe velocities, as well as net positive suction head to ensure system integrity. Overall, careful sizing is essential to maintain fuel quality and ensure reliability in critical operations. This turnover rate chart illustrates the relationship between the required polishing flow and the owner's target turnover window for a 330,000-liter zone. Essentially, the target window set by the owner directly influences the flow rate needed to achieve that turnover. To read the chart, we're using a volume of 330,000 liters and a safety factor of 1.2. For example, if the turnover window is 24 hours, the required flow rate is 275 liters per minute per zone. Increasing the flow to 312 liters per minute shortens the turnover time to about 21.2 hours, while decreasing to 156 liters per minute extends it to roughly 42.3 hours. When it comes to selecting the system design, it's important to choose the nearest standard skid size that exceeds the required flow rate. After that, verify the actual flow delivered, accounting for dirty filter differential pressure and any site piping losses. Also, be cautious not to exceed the media or coalescer's rated speed to avoid damage. In practical terms, for a high-risk Indonesian B40 or B35 storage environment, starting with a 24-hour turnover window is reasonable. You might consider an 8 to 12-hour window only if the owner demands faster fuel recovery or if fuel quality is unreliable. Overall, this chart and the related guidelines help ensure optimal fuel polishing system operation, balancing turnover time with equipment capability and environmental risk. Here, we're looking at a practical sizing example using a 50,000-liter tank. This smaller example is a great way to train engineers before moving on to the more complex case involving 6 tanks of 110,000 liters each. Let's go through the sizing steps. First, we start with the tank volume, which is 50,000 liters. Next, we apply a safety factor of 1.2 to ensure the system can handle slightly more than the nominal volume. The target runtime for polishing is set at 8 hours, which allows for consistent fuel quality maintenance. Using these values, we calculate the flow rate Q by multiplying the tank volume by the safety factor, and then dividing by the total minutes in the target time, 8 hours times 60 minutes. This gives us a flow rate of 125 liters per minute, approximately 33 gallons per minute. From this calculation, the design output is to select a continuous duty fuel polisher that can operate at or above 125 liters per minute at site conditions. It's important to verify that the filter housing and media are rated for this flow and to check pump parameters like suction lift, pipe friction, and differential pressure settings, including any bypass or relief valves. For runtime scheduling, an 8-hour run window is programmed, with some buffer time for sampling and instantaneous contamination monitoring stabilization. An example schedule could be running the system every Tuesday starting at 8 a.m. for 8 to 8.5 hours. The controller should record important parameters such as the selected tank, runtime, flow totals, final ISO cleanliness codes, water and differential pressure status, along with any alarms. Remember, this example uses the formula Q equals volume times safety factor divided by runtime in minutes. While this provides a good sizing estimate, final procurement decisions must validate the hydraulic pump curve and account for filter dirty pressure conditions to ensure reliable operation. Here we focus on how to calculate cleanliness targets using ISO channels and a recirculating tank model. It's important to note that we don't consider one turnover as a perfect pass. This realistic approach ensures more accurate sizing and runtime predictions. Looking at the table, we see initial particle counts and target levels for different ISO sizes. For example, for particles sized 4 microns and above, the initial count is 160,000 particles per milliliter, and the target is 2,500 particles per milliliter. which corresponds to a ratio of 64:1. The ideal number of turnovers needed for this reduction is about 4.16, calculated using the natural logarithm of the ratio. Similar calculations apply to particles 6 microns and 14 microns and larger, with controlling based on the highest required turnovers, about 4.83 turnover cycles. The example runtime calculation assumes a flow rate of 320 liters per minute through a 110,000-liter tank. One tank turnover takes roughly 5.73 hours. Given that effective cleanup requires approximately 4.83 turnovers, the ideal runtime comes to nearly 28 hours. When factoring in a safety factor of 1.2, the planned runtime before final verification extends to around 33 hours. Finally, remember the key rule. Always use actual measured particle counts by channel, assess water status and differential pressure trends, and consider post-polishing sample results. These calculations predict runtime, but do not replace the need for verification to ensure the polishing system's effectiveness. Let's talk about the key considerations for filter sizing and clean pressure drop rules. When sizing filter vessels, it's important to account for factors like flow rate, fuel viscosity, dirt load, and providing adequate maintenance access. Starting with sizing, the rated flow capacity of the filter must always exceed the normal operating flow, allowing for a margin that considers a dirty filter condition and cold fuel viscosity, which increases resistance. Clean pressure drop, or delta P, should be recorded during commissioning. Many filter designs aim for a low clean delta P compared to the bypass setting, helping to optimize efficiency and filter life. Bypass settings are critical for safety and performance. Alarms and trips should be configured well below the bypass pressure to avoid relying on bypass operation under normal conditions. Element collapse pressure must never be exceeded, so high differential pressure sensors should be in place to protect both the housing and filter elements. When selecting filter media, focus on the beta ratio and micron rating rather than just the nominal size to ensure proper filtration performance. Dirt holding capacity needs to be estimated based on the expected contamination load and desired maintenance intervals to avoid frequent changes. For water removal, the element must be sized to handle expected water ingress and fit into the existing drain strategy. Viscosity correction is also important because cold diesel fuel can significantly increase pressure drop. Always apply the manufacturer's correction factors before setting alarms to prevent false triggers. After any element change, be sure to vent, leak check, and establish a new clean delta P baseline under stable flow conditions to ensure accurate performance monitoring. Finally, always refer to the approved datasheet for final settings like bypass pressures and element collapse values to ensure compliance and safety. Before moving forward with procurement or commissioning of a mission-critical fuel polishing skid, it's essential to go through this sizing checklist to ensure everything is properly addressed. First, consider the tank volume. You need to know exactly which volume must be polished. Is it the usable volume, the total, or some owner-defined reserve? This should be verified against the tank schedule or design basis documents. Next, define the turnover target. How many hours are required for a complete turnover, and how often should this process occur? This is typically determined by the owner's standards or their operations and maintenance strategy. Then evaluate the pump flow. It's critical that the pump can deliver the necessary flow even under challenging conditions, such as at cold fuel viscosity and when the filter is dirty, which causes differential pressure. Check this against the pump curve and available motor torque. Filter capacity is another key factor. The filter must be rated to handle the expected flow and contaminant load, which can be confirmed through datasheets, beta ratio, and dirt capacity ratings. For sampling, ensure there is an ICM sample point located after the final filter and that flow conditions at this point are stable. This can be verified during commissioning via sample loop tests. Controls must be thoroughly checked. Confirm that permissives, alarms, and building management system points are mapped accurately, supported by an input-output list and functional testing. Containment is crucial for safety and environmental compliance. The skid should be able to contain any maintenance or gasket leak volumes, which you can verify through bund volume calculations. Finally, consider maintenance accessibility. Can filter elements be removed safely while isolating and draining the system? This requires a detailed access review and method statement to ensure safe procedures. Following this checklist helps guarantee that the fuel polishing system will operate reliably and meet both operational demands and safety standards. In this section, we'll focus on the operation, maintenance, and troubleshooting of the data center fuel polishing system. We'll cover daily checks and monitoring for alarms, which are crucial to ensure the system runs smoothly and safely. Preventive maintenance is another key area, helping us avoid unexpected failures by following a structured schedule. We'll also review the operator checklist designed for safe polishing practices, along with commissioning and acceptance checks to verify the system's readiness. Finally, we'll go through a troubleshooting matrix that addresses common alarms, enabling quick identification and resolution of issues. This comprehensive approach ensures the fuel polishing system remains reliable and effective. Before starting the polishing process, it's crucial to complete a thorough operator checklist to ensure safety and efficiency. First, confirm the tank status. Make sure the selected underground storage tank is available, has the correct fuel level, and there are no conflicts with fuel transfer or maintenance lockouts. Next, check valve alignment. Manual isolation valves should be set correctly, and solenoids must be operational with proper feedback confirming their status. Then assess the skid condition. There should be no standing fuel in the bund. The drain valve must be closed. Leak switches need to function properly, and there should be no odor or visible seepage. Moving on, evaluate the filter condition. Differential pressure should be below the threshold. There should be no signs of filter bypass, and all drains, vents, and housings must be securely closed. The pump and variable speed drive require attention as well. Confirm the correct pump is selected. The VSD is healthy with no overload issues, and speed limits are properly configured. For the ICM and sample loop, verify the monitor's health, ensure sample pressure and flow are available, and check for any leaks or airlocks in the sample line. Lastly, review the HMI and BMS settings. The system should be in the correct mode. Alarm conditions should be acknowledged only after their causes have been addressed, and trends must be actively recording. Remember, the start command should only be given after all these mechanical and control permissives have been verified to maintain safe and effective operations. When we talk about commissioning and acceptance tests, the main goal is to ensure both the hydraulic performance and the control response meet the required standards. This means that the system not only operates correctly under pressure, but also responds accurately to control inputs. Looking at the specific tests, the hydrostatic or leak test verifies that there are no leaks in critical components like the skid, filter housings, sample loops, valves, and drains. For valves, the valve-proof test confirms that they provide the correct open or closed feedback, and that any wrong state triggers an interlock to prevent errors. The pump run test ensures that the flow meets the set point, the variable speed drive maintains stable speed and current, and there's no cavitation in the pump. Filter clean differential pressure is recorded at a reference flow and temperature to establish a baseline for monitoring filter condition over time. Alarm tests are crucial for safety and reliability. The differential pressure alarm test checks that warnings and maintenance alerts work properly, including high alarm actions. The leak alarm test confirms that if a leak is detected, pumps stop, valves close, and alarms activate on both the HMI and the building management system, with a proper reset procedure in place. The integrated control module test for fuel polishing verifies sample flow and pressure, and confirms that ISO cleanliness results are displayed and logged correctly. When it comes to system integration, all critical alarms and trends must be properly mapped and time-stamped within the building management system or distributed control system. Finally, the emergency stop test assures a safe shutdown and a controlled restart, ensuring the whole system handles emergency situations smoothly. Through these thorough checks, we can confidently verify set points, monitor sample pressure, confirm filter integrity, and ensure the fuel polishing system operates safely and efficiently. Here we have a detailed preventive maintenance schedule designed to ensure optimal performance and reliability of the fuel polishing system. It's important to follow site procedures, manufacturer manuals, and fuel condition trends when determining actual maintenance intervals. Daily or per shift, operators need to review HMI alarms, pump status, selected tanks, flow rates, differential pressures, leak trays, and the latest ISO cleanliness results. Weekly tasks include running any scheduled polishing if not automated, and inspecting the skid, valves, sample lines, drains, and containment areas for any issues. On a monthly basis, Trending differential pressure and ISO codes is crucial, along with testing the leak switch if it's safe to do so, and checking flow, pressure, and alarm transmissions to the BMS. Quarterly maintenance focuses on inspecting filter housings, seals, valve actuators, as well as reviewing VSD and MCC logs, and performing housekeeping around the skid. Every 6 months, a review of lab fuel samples, evaluation of water and microbial risks, tank bottom inspections, and updating the corrective polishing plan are necessary. Annually, there should be a comprehensive review of emergency power fuel quality, functional tests of interlocks, and recalibration or verification of instruments according to procedure. Condition-based maintenance must be performed when specific triggers like differential pressure, water loading, or flow failures indicate it's time to replace or clean filters. On the documentation side, after every media change, it's essential to record comprehensive details such as the date, tank or source, old and new differential pressures, the type of filter element used, reason for replacement, and the operator's initials. Likewise, after any cleanliness alarm, the affected tank should remain flagged until a successful repolish or lab confirmation clears the issue. Maintaining this thorough schedule and documentation process provides solid evidence of maintenance efforts and ensures the fuel polishing system operates safely and efficiently. Here we have a troubleshooting matrix designed to help quickly identify and resolve issues in the fuel polishing system. The key idea here is to use the symptoms you observe to isolate whether the problem is related to hydraulics, contamination, controls, or maintenance activities. For example, if the pump starts but there's no flow, this might be caused by a closed valve, an air lock, an empty suction line, a failed pump, or a blocked strainer. Immediate checks should include verifying the tank level, valve feedback, suction pressure, and ensuring the pump is properly primed along with checking the strainer for blockages. If you notice unstable flow, potential causes could be air entering the system, cavitation, variable speed drive hunting, or a restriction in the sample loop. It's important to inspect suction joints, monitor pressure trends, check the VSD limits, and verify the bypass line. A quick rise in differential pressure, or DP, often indicates heavy sediment buildup, water in the filter element, use of the wrong media, or microbial sludge. Here you should inspect the tank's condition, check any water alarms, look at the element type, and review recent fuel deliveries. When the ISO cleanliness code remains high, it often points to poor mixing, incorrect sample points, damaged or bypassed filters, or sludge in the tank. The recommended actions are to confirm the sample location, test filter integrity, perform multiple turnover runs, and send samples to the lab for analysis. For water alarms, potential causes include tank water accumulation, emulsified water, or saturated water media. Draining the water, inspecting the bottom sample, and replacing the water media are the key remedies. Leak alarms generally indicate a gasket, seal, or joint leak, or tray liquid issues. It's crucial to stop or isolate the system, inspect the tray, make repairs, and only reset the alarm after a successful leak test. Finally, if the ICM shows no result, this might be due to no sample flow, power or communication faults, alarm settings, or a plugged sample line. Checking the pressure gauge, flow settings, wiring, ICM status, and communication mapping will help resolve this. This matrix is a valuable tool that helps streamline diagnostics and ensures that operators can respond effectively to maintain optimal system performance. Here we have the concept of a readiness evidence log, which is crucial for mission-critical systems. Essentially, a system is only considered mission-critical if we can actually prove its readiness. That's why tracking and documenting evidence is so important. Let's look at the core elements in the evidence log. The date and time show how recent the readiness check is, ensuring we're working with current information. The tank ID helps us avoid mixing data between tanks, so we don't overlook risks in any individual tank. Polished volume confirms that enough fuel was circulated to make the test meaningful. Flow rate and runtime verify that the turnover calculations and pump performance are accurate. The filter differential pressure, or filter DP, gives insight into the filter's condition and helps us monitor maintenance trends. ISO code, or particle count, records track particle cleanliness over time, which is critical for fuel quality. Water status indicates potential risks from free or emulsified water and shows what actions have been taken. Alarm status confirms that no critical defects remain active, and corrective action records link any alarms to the necessary repairs, media changes, or sampling evidence. Finally, the operator or technician's name provides accountability and traceability, ensuring responsibility is clear. One important point is that the HMI status only becomes valid readiness evidence when it's trended and reviewed over time. For best results, it's recommended to store this data locally on the HMI, as well as in a building management system or distributed control system for trend analysis, and to export maintenance records. Key performance indicators to watch include the percentage of tanks meeting cleanliness targets within required intervals and tracking days since the last filter media change, along with the clean baseline filter differential pressure. This thorough logging and analysis process helps guarantee that your fuel polishing system remains reliable and ready when you need it most. In this training exercise, we are going to diagnose a polishing alarm in the fuel polishing system. The scenario involves Zone A polishing underground storage tank 3 at a flow rate of 156 liters per minute. After 6 hours, we notice that the differential pressure rises sharply, the flow rate drops below the set point, and the integrity control module reports a worse ISO code than in the previous run. Interestingly, there is no leak alarm active in this situation. Now, let's think about what could be causing this issue. The most likely causes include heavy sediment, water, or microbial sludge building up in the media, using the wrong type of media, a valve that is partially closed, or some disturbance inside the tank. To investigate this further, the first readings we should check are the differential pressure, suction and discharge pressure, flow rate, valve feedback signals, any water alarms, the filter drain status, the sample loop pressure, and the condition at the bottom of the tank. It's important to remember not to mark the tank as complete until both the polished volume and cleanliness criteria have been fully satisfied. For maintenance, you should plan to replace the filter media, conduct a thorough tank investigation, and take post-maintenance baseline cleanliness recordings to ensure everything is back to optimal condition before returning the system to automatic service. This approach will help diagnose and resolve polishing alarms effectively, maintaining fuel quality and system reliability. Let's go over the key takeaways for fuel polishing systems. First, it's important to remember that fuel polishing is more than just a filter skid. It's a comprehensive readiness system. When it comes to design, we need to size the flow to achieve the required turnover and verify that pump and filter ratings can handle the worst-case fuel conditions. In terms of filtration, it's best to use staged media, consider the beta ratio, implement a water control strategy, and continuously monitor differential pressure to keep the filters performing optimally. Controls play a crucial role as well. The PLC and HMI must manage tank sequencing, verify the operation of valves, pumps, and flow, and alert operators to any issues with differential pressure, leaks, water presence, or cleanliness faults. Cleanliness monitoring is essential, so use the ISO 4406 particle code along with inline monitoring systems and periodic lab testing to confirm fuel condition. For containment, having a bund skid with controlled drainage to an interceptor is necessary to manage any gasket or maintenance-related leaks. Lastly, evidence of readiness comes from maintaining detailed records, including tank-specific volume measurements, ISO cleanliness codes, differential pressure data, water detection, and alarm history. These elements together ensure the fuel polishing system keeps the fuel in optimal condition and ready for use at all times. Here are the key references and source notes for this technical training module. The content here is based on several important inputs, including the Fuel System Tier 3 O&M Manual, training minutes, and prior fuel polishing training modules. We've also incorporated user guides, wiring manuals, and technical notes related to fuel polishing, ensuring the material is comprehensive and accurate. In addition, the standards and public technical references supporting this module are crucial. These include Indonesia's mandatory B40 biodiesel program and biodiesel allocation targets for 2025, banking regulations on IT and disaster recovery, as well as internationally recognized frameworks like NFPA 110 for fuel quality testing, ASTM standards for diesel fuel quality, and ISO contamination coding. Together, these standards help ensure best practices and regulatory compliance. It's important to highlight that this training material is vendor neutral. Any pictures of equipment shown are for visual reference only and do not imply endorsement of any particular brand or vendor. Also, whenever you use or apply the information here, make sure to verify final values with the specific owner specifications, local authorities having jurisdiction, OEM manuals, and the engineer of record. Finally, regarding design verification, the sizing examples provided are strictly for training purposes. They should not be used for procurement without thorough checks against pump curves, filter differential pressures, suction conditions, voltage limits, control requirements, and site-specific safety and procedural considerations. This ensures all installations are safe, compliant, and optimized for their specific applications. Now, let's take a closer look at Appendix A, which is a calculation worksheet designed to help size or audit a fuel polishing system. This worksheet guides us through a step-by-step process using specific input values and formulas. We start with the tank volume, represented as V. In the example, the tank volume is 110,000 liters per underground storage tank. Next, we account for the number of tanks in a zone. Here we have 3 tanks, totaling 330,000 liters. The target turnover time, or how frequently the total volume needs to be processed, is typically 24 hours, or it could be based on the owner's criteria. Using this, we calculate the required flow rate, Q, which is the volume divided by the product of turnover time and minutes per hour. In the example, this results in 229 liters per minute. Then, we compare this with the selected pump flow rate, which might be 156 or 312 liters per minute. Using the actual pump flow, we determine the actual turnover time by dividing the total volume by the product of the pump flow and minutes per hour. For instance, with 156 liters per minute, the turnover is about 35.26 hours. The number of turnovers required depends on the cleanliness target or trend of the system. Multiplying the turnover time by the number of turnovers gives us the total runtime. In the example, 2 turnovers at 156 liters per minute equals 70.5 hours. Finally, it's important to check the filters for flow, clean and dirty differential pressure, beta ratio, and water capacity to ensure proper operation. Controls also need to be reviewed, including the flow totalizer, differential pressure alarms, ICM results, and leak detection logic. This worksheet is a valuable tool to ensure the fuel polishing system is appropriately sized and operating efficiently to maintain fuel integrity. Here we have Appendix B, which serves as a specification checklist for a complete fuel polishing skid. This checklist ensures that all critical components and parameters are properly defined for optimal system performance. Starting with the hydraulic category, it is essential to specify flow rate, operating pressure, suction lift, diesel temperature and viscosity, net positive suction head, and relief or bypass protection. These factors directly impact the hydraulic performance and reliability of the system. Next, for the pump, we need to specify the type, such as a positive displacement gear pump, along with motor kilowatt rating, the use of a variable speed drive, the duty and standby pump philosophy, seal materials, and run-hour tracking capabilities. These details affect how efficiently and reliably the pump operates. The filter section requires specification of the number of stages, micron or beta rating, water removal media type, the pressure differential between clean and dirty filters, bypass or collapse limits, and access to filter elements for maintenance. Proper filter specification is vital to ensure effective contaminant removal and system uptime. Instrumentation includes flow meters, totalizers, pressure and differential pressure transmitters, water sensors, integrated control modules, leak detectors, and valve position feedback. Accurate instrumentation allows for precise monitoring and control of the polishing system. Control specifications encompass the programmable logic controller, human-machine interface, timers, tank sequencing, minimum volume settings, alarms, interlocks, security of settings, and integration with building management or distributed control systems. These control elements are crucial for safe, automated operation and system integration. Containment must consider features like bund skid trays, retention volume capacity, leak detection switches, normally closed drain valves, and routes for interceptor discharge, all designed to manage leaks and spills safely. For maintenance, specifying isolation, drain and vent valves, sample ports, spare filter elements, calibration plans, and cleaning procedures ensures the system remains serviceable and reliable throughout its life cycle. Finally, documentation is key and should include piping and instrumentation diagrams, input-output lists, cause and effect analysis, functional test procedures, operation and maintenance manuals, and training along with readiness log templates to provide comprehensive support for system operation and troubleshooting. This checklist comprehensively covers all minimum items to specify, helping to ensure that every aspect of a fuel polishing skid is accounted for, which is critical for maintaining fuel quality and equipment reliability in data center operations. Here we have a sample cause and effect matrix presented in Appendix C, designed specifically for the data center fuel polishing system. This matrix is a useful tool that you can customize to fit the final functional design of the PLC. The matrix clearly maps various causes, such as alarms or faults, to the corresponding actions that need to be taken, including stopping pumps, closing solenoids, triggering alarms on the HMI and BMS/DCS, and setting maintenance flags. For example, if a leak tray alarm occurs, the system will stop the pump, close solenoids, set high-priority alarms on both the HMI and BMS/DCS, and activate the maintenance flag. Similarly, a high filter differential pressure will prompt similar responses, indicating the criticality of these conditions. Other conditions like a low flow after delay result in stopping the pump and possibly closing solenoids, along with alarms and maintenance notifications. Some faults, like the VSD or MCC fault, are handled by ensuring the pump has already stopped, with solenoids closing as required. This matrix helps ensure safety and proper maintenance by defining clear, prioritized responses to various system alarms and warnings. You can adapt this template to meet the specific requirements of your system and facilitate effective operational control and monitoring. This concludes our training module on the fuel polishing system. Remember, the key to readiness lies in a few essential principles: maintaining clean fuel, ensuring controlled circulation, verifying all instrumentation accurately, containing any leaks promptly, and keeping thorough documentation as evidence. These practices ensure the system operates efficiently and safely. Thank you for your attention throughout this module.